Hello, everyone, and thank you for joining today's John Bahcall colloquium. I'm Marcus Hahn, senior research scientist at SURF here. So a few quick housekeeping notes before we begin. Today's talk will be about 40 minutes, followed by 10-15 minutes of Q&A. Oh, did I touch your slides? I'm sorry. And then you can ask questions live by raising your hand in Zoom or by using the Q&A button. This talk is being recorded and will be available at institute.surf/JBC, as well as on Surf's YouTube and Vimeo channels. To receive notifications about upcoming talks, visit the Connect link at the top of the institute.surf webpage. You can register for all scheduled talks at institute.surf/JBC. We now have a dedicated Slack channel to continue the conversation after each colloquium or to follow up later. A link to the Slack channel is in the Zoom chat. You're welcome to ask additional questions of the speaker or engage the broader group assembled there. The featured speaker will be available on Slack for up to 30 minutes following the talk. Now it's my pleasure to introduce today's speaker. Dr. Balantekin received his PhD from Yale University. After working at MIT and Oak Ridge, he joined the faculty of University of Wisconsin-Madison, where he is now the Eugene P. Wigner Professor of Physics. Balantekin was selected as a presidential young investigator in 1987. He has received the Wisconsin Alumni Research Foundation Kellett Mid-Career Award, the Alexander von Humboldt Foundation Senior Scientist Award, and the Distinguished Service Award of the Division of Nuclear Physics of the American Physical Society. He also received the Breakthrough Prize in Fundamental Physics, together with Daya Bay and Prospect collaborations, and the Hans R. Bethe Prize of the APS. Balantekin served as the chair of the DNP and on the executive board of the APS. He served as the editor of Journal of Physics G, Physical Review C, and Physics Letters B. He's a fellow of the American Physical Society and the Institute of Physics of the United Kingdom, as well as a member of the Turkish Science Academy. That's quite a lot. All right, so let's welcome Dr.
Well, thank you. Thank you very much. I hope you can all hear me, and I hope you can also hear on the Zoom. Well, okay, today I want to tell you where we started, and then we'll see where we go to many trillions of neutrinos. Well, this is July. So it's an appropriate picture. We are basically a revolution, in a revolution in astrophysics and cosmology. But just like Washington, where scientists are just crossing Delaware, there is a long, long travel ahead of us. And this revolution actually started right here under the city. And you can see the open pit. So that revolution started here half a century ago. Now, what is the revolution? For many centuries, we were only able to look at the sky and see what our eyes can see. Of course, this generated centuries of folklore and literature. So, for example, Shakespeare said, "It is the stars. The stars above us govern our conditions," from King Lear. Or perhaps the fault, dear Brutus, is not in our stars, but in ourselves, which is a more correct statement. And then, of course, again, another July thing is the Tanabata Festival, which is celebrated in China and Japan. And basically, there are two deities, Orihime and Hikoboshi. And according to legend, the Milky Way, in Japanese, it's a river of stars, separates these two lovers. And they are allowed to meet only once a year in July today. So this is appropriate. But, you know, I grew up in a big city. You could not see, forget about Milky Way, you could not see even most of the stars. The very first time I saw the Milky Way was when I was in a summer school at Les Houches and high in Alps. And it was absolutely magnificent. I mean, the majesty was great, but little that I knew at the time, this was a long time ago, little that I knew at the time, I really only saw part of the majesty of the heavens, because the A lot of stuff we just cannot see with our own eyes. Our own eyes are very, very, very specific. So gradually, scientists uncovered many other messengers of the cosmos, including neutrinos, radio waves, and gravitational waves. This multi-messenger approach was truly revolutionary in astrophysics. And as I said, a revolution which actually started right here with the experiments of Ray Davis, supported by the theory work of John Bahcall. Now, Davis was able to catch only a small number of neutrinos. It's amazing. If you look at his data, it's revolutionary, but just a few neutrinos as you go on. But this very small number led to fundamental questions about the subjects, like the nature of mass, precise details of the evolution of the stars, and the possibility of detecting very far sources by high energy neutrinos which can travel and carry information over very, very, very long distances. So that was essentially a significant step. Well, okay, what was Davis trying to measure? What Davis was trying to measure, in an old question, where does the energy of the sun come from? Originally, in 19th century, people thought, like von Helmholtz thought, that the energy is gravitational. So sun shrinks. As it shrinks, the binding energy, gravitational binding energy, is converted into photons, and it comes and heats us and grows our vegetables and plants and so on. But there was a problem with that. We knew more or less how large the sun was. We could measure, and then you can actually estimate its mass. So if you convert that mass into gravitational energy, it will run out of fuel in about 200,000 years. Already, we had enough evidence that the Earth is much older than that. And so that, Earth cannot be older than the sun. So in 1920s, after Einstein came up with E equal to mc squared, Sir Arthur Eddington said that, well, what powers the sun is the nuclear fusion. Basically, nuclear fusion converts the energy, mass into energy, binding energy. And in 1938, Hans Bethe basically discovered the precise mechanism for doing that. So he is the first one who actually understood why the stars shine. Then in 1946, Pontecorvo came up with the idea of using chlorine as a detector, and also the idea of neutrino oscillations. And in 1964, Davis actually built a chlorine detector here at the Homestake mine, and he and Bahcall had the standard solar model. Now, so the goal of Davis was to detect these neutrinos that come from these nuclear reactions that power the sun. So those three gentlemen, Hans Bethe, John Bahcall, and Ray Davis, actually set out to do this. And John and Ray published a paper two papers back to back in his Rev Letters in 1964, where they declared that their goal was to see into the interior of a star and thus verify directly the hypothesis of nuclear energy generation. So that really was a revolutionary step, that you can actually observe the universe not just with the visible light. Well, after several other additional experiments, the flux and the composition of the solar neutrinos is now well known. We actually had a workshop even before there was a talk of an underground lab here at the Institute of Nuclear Theory in Seattle in spring of 1994. And you see the proceedings of that workshop, where we decided that it's probably a good idea to have periodic deep updates of the solar modeling data. And today, we already have 3 more such workshops. Each time, we were improving our understanding of the stars. And these contributions to the theory of main sequence stars, which is Sun is a main sequence star, were really made possible in part by the work of Bahcall and Davis. So that's where the entire neutrino business started. And of course, now we know neutrinos come from all sorts of stuff. You know, there are neutrinos left over from the early universe, neutrinos from the sun, from the supernova, from the reactors, from underground, from inside the Earth, because there are a lot of radioactive elements in the Earth, in the atmosphere, and so on and so on. So, where do the trillions of neutrinos come from? Beside the sun, the core collapse supernova are produced of large numbers of neutrinos, and that will be detected, hopefully, at the Dune detector here, if we are lucky, because you cannot order a supernova to explode, you just have to wait for it. And if we are lucky while the detector is running, we will see those neutrinos. So, this is a diagram that actually shows you evolution of main sequence stars. It's actually more of a cartoon, but it is a reproduction of a diagram that scientists call Hertzsprung-Russell diagram. It actually shows you what the evolution of the stars go like, and eventually you go to carbon, etc. And then when you reach to that level, there is nothing that would hold the gravity in bay. Normally, in a star, gravity is counterbalanced by the energy coming from these nuclear reactions. So there is a balance there. The star is in balance. Eventually, once you run out of the fuel in the star, there is nothing to balance the gravitational push, and the star collapses onto itself. And that is what we call core collapse supernova, because it collapses from the very center. And these core collapse supernova produce very large numbers of neutrinos, something like 10 to the 57 or so neutrinos per each event. That's a lot of neutrinos as compared to the 3 neutrinos, 4 neutrinos Davis was able to see every year. But that's where he started. So you see, actually, on the left there, with the Japanese writing, it says background. That is the neutrinos as a function of time coming from the supernova 1987A. And on the right in the diagram, you see the different detectors, what they had observed. The amazing thing, though, this detector Kamioka was not finished. It was actually a very interesting idea. It was not built to detect neutrinos. It was an accidental detection, because they were trying to see if the matter is stable. The theories of physics called grand unified theories predicted that protons decay. They decay by emitting photons. So they built a proton decay detector. So you have a source of protons, and experiments are not cheap, and everyone knows. So the source of protons has to be cheap. The cheapest source of protons is water. So they put water in a big tank with the phototubes around that to detect the photons coming from the proton decay. Well, they did not really see protons decaying, but what they saw, that there was a background, a noise that they really was not too happy about. That was the solar neutrinos that Ray first detected. Those solar neutrinos was the background. So in January of 1987, they made a decision, what every good experimentalist would do. If your signal is too weak as compared to your background, you just switch them. You start detecting the background. So in February of 1987, they were just starting to detect the solar neutrino background. And it was not the conversion, it required some conversion of the instruments. The conversion was not finished. So when the supernova went on, the timing wasn't there. So what you see at the time is the wristwatch of the graduate student who was on a night shift at the time. But nevertheless, so the numbers may not be working, but nevertheless, these neutrinos come from core collapse supernova. The catch is, if you want to catch a supernova with its neutrinos, you'd better know what neutrinos do inside the star. I mean, this is a great picture. I hope there are baseball fans here. Great picture from the Symmetry magazine. Now, supernova releases a lot of energy. It's like 10 to the 59 MeV of energy, and about 1%, at most 1% of that energy is what you see as light. The 99% of this energy carried away by neutrinos and antineutrinos. So altogether, you're talking about 10 to the 57 neutrinos, a very large number. What that means is that even though neutrinos interact with each other very weakly, very feebly, the density is so high, you cannot avoid neutrino-neutrino interactions. And that actually, of course, leads to novel collective and emergent effects, such as conserved quantities and interesting features in the neutrino energy spectra. Now, I think I would like to put everything in a better view. So if you look at the many body systems around what we study in physics, nuclei have at most about 200 particles. And the driving interaction is strong interaction. In condensed matter cases, you have a driving interaction, which is electromagnetic, but you have at most an Avogadro number of particles, but most of the time it's just a few thousand particles at most. So neutrinos in the supernova is driving interaction is weak, and you talk about 10 to the 57 neutrinos. Now, this is what we call the standard model of particle physics. This is not like a new theory of physics, it's an existing theory. But the neutrino and neutrino interaction, there is no way we can test in any other setting. So this is a really good example that astrophysical extremes allowing us to test physics that you cannot test in any other way. Now, another related question is formation of elements. So you can say how one actually cooks the elements around us. I mean, those of you read comics would recognize characters from Asterix. So how do you do that? Well, we know from Hans Bethe's work that energy is released by fusion when you fuse nuclei in the stars. And all the way to iron peak, you can actually create elements up to iron peak, iron, cobalt, nickel, and so on. But once you reach to iron, not iron, but iron, nickel, cobalt, it's actually an isotope of nickel, but not too many people think about nickel, so iron core. Once you reach the iron, you reach the ground state of the universe. It is the most bound nucleus, most bound nuclei are in that area. So you can no longer fuse those nuclei and extract energy to convert the elements into one another. So you need a new method once you exceed the mass number of iron class nuclei. You need a different method, and that is the so-called R process or S process. So the Big Bang produces just only really two elements, hydrogen and helium, really in greater numbers. And then a little bit of deuterium, a little bit of lithium, and a little bit of beryllium. That's it. So then once you form these elements, then they gravitationally pull together, form real giant, huge stars. Those are what astronomers call population 3 stars. They're very big, and they include essentially nothing but hydrogen and helium. They're huge stars. Because they are so huge, inside temperature is very high, so they burn very quickly. So their lives are very short. But during the short life, they produce elements up to iron level. They go supernova and distribute those elements up to iron, nickel, cobalt, and so on. So once you actually reach to that level, you can no longer produce elements in the regular stellar evolution. So what happens is then you form new stars from the debris of the first stars, and these are so-called population 2 stars. They still don't have too much besides hydrogen and helium, but they're not as big. so they live a bit longer. Some of them go supernova. They produce uranium, europium, thorium, etc. via so-called R process. And some of them produce other elements via the so-called S process. What are these two R and S processes? Well, R process, R is for rapid, and S process, S is for slow. So this is a process where a core nucleus, initial nucleus, keeps capturing neutrons. You can either capture them very rapidly, so that it becomes R process or the rapid process, and that's a very catastrophic event. That can happen during the supernova explosions or also during the neutron star mergers. Or you can capture very, very slowly, over like tens of thousands of years, and that's the S process. So those actually give rise to slightly different nuclei. Well, it turns out there is an intermediate process, the so-called I process. That is neither too fast nor too slow. And we will see that neutrinos do that too. So neutrinos not only play a crucial role in the dynamics of these sites, but they also control the value of electron fraction, which is the parameter that determines the yields of these nucleosynthesis events. You see on the top there, the elements produced in different places in the Big Bang, all the stars by our process, and what we actually see in the solar system. And there are two possible sites to produce these heavier elements. There's either supernova or neutron star mergers. There's a lot of argument which is the right size and so on. I'm not going to get into that, but they are both possible. So here's a cartoon of what happens to neutrinos. Well, neutrinos are produced because the star collapses and has its entire binding energy of the initial pre-supernova star, gravitational binding energy. So the star is very, very hot. Well, in the summer, when you are hot, what do? You sweat, because that's a good way to get rid of energy. The star sweats by forming neutrino-antineutrino pairs. So that's how 10 to the 57 neutrinos come from gravitational binding energy of the original pre-supernova star. So then these neutrinos, of course, eventually reach to us. But when they are first formed at the very center of the star, these neutrinos the density is so high, their interactions are very strong, that it's not easy for them to move freely. They are not so-called free streaming. They start free streaming a little bit in a region that we call neutrinosphere. And then in that area, neutrinos scatter from one another. They are still free streaming, but they are scattering from other neutrinos because the neutrino density is very high. So the oscillations of neutrinos is called collective oscillations because many neutrinos take place in that. Then once the neutrinos go a little bit further out, then the neutrino density goes down. So neutrinos can no longer scatter from other neutrinos, but they do scatter from the other stuff in the star, like electrons, protons, and the nuclei, and so on. So they scatter from the background particles. That's a so-called MSW oscillations. And that's a region where neutrino density is very low. So there is this region of different oscillations in the star. As I showed you earlier, that those neutrinos do interact with each other. And how do you actually describe that interaction? Now I'm going to write just a few equations, not too many. So you introduce the density operator. On the top of the yellow range of the slide, the psi's are the states of the system, and p psi, the probability of the system to be in that state psi, and you form that combination and sum over all possible states. So that density matrix is calculated by solving an equation shown in the middle of the slide. It's a first order differential equation. It looks incredibly simple, but it's incredibly difficult to solve. It is not that easy. So typically, the Hamiltonian of the equation includes the neutrino mixing, forward scattering of neutrinos of other background particles, and forward scattering of neutrinos from each other. And then there are collisions. Now, in principle, there is no reason to separate collisions from the original reactions, but that's done in a semi-classical way to simplify the problem. Obviously, eventually you put the collisions together with the Hamiltonian and calculate the whole thing. So, why is this interesting? Because there is a lot of interest these days in quantum information science. In quantum information science, you try to describe quantum mechanics using objects called qubits. Qubits have two states. Well, typically, when you talk about qubits in quantum computing, quantum information science, you're talking about spins, ordinary electron spin, because they also have two states, either spin up or spin down. And that, of course, explains a lot of chemistry and so on. But if you say there are only two flavors of neutrinos, not three, but only two, then you can say those two flavors are spin up and spin down directions in an isospin space. And then you can actually map two flavor neutrinos onto a qubit. So then you can actually use the entire method of the quantum information science. Many times, these calculations are done in the so-called mean field approximation. What mean field says, each neutrino moves independent of others, but interacts with the overall mean field created by all other neutrinos. Whereas you can also talk about many-body. You can say you can include momentum changing interactions, but they vanish in the mean field limit. So you only consider forward scattering most of the time. Now, number of neutrinos is irrelevant in the mean field approximation, since it's basically a one-body limit. So when you talk about core collapse supernova in the mean field approximation, you don't have to worry about 10 to the 57 neutrinos. Just a single neutrino happily goes through some fog of all other neutrinos. It's still non-trivial because it's still a nonlinear problem, but it's not that difficult. So, well, how do you do that? There are two possibilities. One is solve the exact problem for a small number of neutrinos. And of course, computational difficulty increases as you increase the number of neutrinos, and you look for some sort of scaling behavior, if you can find it. So at each step, you have to test how much the many-body solution differs from the mean field solution, and that's the path we took at Wisconsin. One can also try to estimate the large N limit from thermodynamic considerations, or you can try to formulate in many-body physics in other ways. In particular, one possible, very popular one is higher order truncation of the many-body combinants. So you say, okay, the combinant of third order is zero, because in general, in many-body physics, as interactions go on, higher and higher order combinants will be smaller and smaller. So the small combinant you set to zero, and then you only calculate the lower order combinants, and that's actually not a bad approximation either, and that was first proposed by Christina Volpe. Now, what is going on? A system of n interacting particles, each of which can occupy k states. That's the problem we're talking about. K is the number of flavors, n is the number of neutrinos. Well, you can actually solve this problem exactly if you can. It's impossible to enter the 10 to the 47 neutrinos. If you can, you have a wave function which includes all the states, entangled states and unentangled states. Entangled means the states interact, remember one another. And the dimension of that Hilbert space is k to the power n. And you can imagine, even for two flavors and say 100 neutrinos, 2 to the 100 by 2 to the 100 Hilbert space is very, very difficult to put on classical computers. Or you can actually do the mean field approximation. You forget about entanglement between neutrinos, only unentangled states, and then dimension of space gets much smaller, k times n. So if you have three flavors and say 100 neutrinos, 200 by 300 by 300, you can easily put on a classical computer. And that's why people do the mean field approximation. And there is something called von Neumann entropy. It was introduced a long time ago during the World War II by von Neumann. And here it's given there in the yellow at the bottom of the slide. And if a state is pure, that is to say, if the system is in a single state, let's say you have a harmonic oscillator, it's only in the ground state, then it's a pure state. Or the system may occupy multiple states at the same time, then it's not a pure state. For a pure state, the square of the density matrix is the same as density matrix. Once you take that assumption and then put into von Neumann entropy, you see that the von Neumann entropy has to vanish. If rho square equal to rho, that trace of rho log rho is 0. You can show that. It's a simple math exercise. But if a state is mixed, once you square the density matrix, it's no longer equal to itself. So then von Neumann entropy is different than 0. So von Neumann entropy is a measure of the entanglement of the system. And that is that's what quantum information science is telling us. Now, there are many techniques to do exact evolution. There's something called Beta ansatz. Beta did other things besides figuring out how the stars shine. He also figured out how to solve certain mathematical Hamiltonians, and then he introduced this method called Beta ansatz. You can actually do the Beta ansatz method that Beta introduced, but it has numerical instabilities as you increase the number of neutrinos, and you go to about 10 or 15 neutrinos. However, it's very valuable because it gives you conserved quantities. You know what has to be the same as neutrinos are transported. That's very, very important because then you can test all your exact calculations to see how good they are by checking the conserved quantities. If the conserved quantity is no longer the same as the original value, you know that you did something wrong. You are using the wrong technique to calculate the evolution. So then there are things called tensor network techniques. These are introduced in condensed matter physics. Or you can actually use noisy quantum computers. Well, I'll tell you what it means that they are noisy, but what basically it means they don't work very well. They should be improved eventually. Okay. So, and the computation time, of course, depends on what kind of techniques that you use. Now, if you have a single qubit, the density matrix is shown at the bottom of that. So that is 1/2 1 plus sigma dot p. P is the so-called polarization vector. Sigma is the Pauli matrices, and the density matrix has to be Hermitian. So you can actually easily write down. You can show that that density matrix, its trace is 1. The density matrix trace has to be 1, and then it's Hermitian. Now, if the state is pure, if rho square equal to rho, you can also show, just calculate rho square from that, you can also show that the absolute value of the polarization vector has to be 1, or p squared has to be 1. So p is a three-dimensional vector. Well, the three-dimensional vector square is equal to a constant that describes a sphere. And that's called Bloch sphere. And in the Bloch sphere, if you have only 2 flavors, electron neutrino is on the top and in the north pole, and the muon neutrino is in the south pole. So that's actually the terminology of quantum information science. So you can actually do these calculations. These are calculations on a classical computer trying to solve the evolution of evolution of the system. So you can see the top graph is the polarization, the third component of the polarization vector as a function of the number of neutrinos, the final value of the polarization vector, far away from the center of the star. And as you can see, there is a deviation from the many body and mean field. There's a deviation between many body and mean field calculations. That's fine, but it's probably better to calculate the entropy itself, the von Neumann entropy. The bottom panel shows you the von Neumann entropy as a function of the distance from the center of the star in some funny units. And you can see as you increase the number of neutrinos, these are just neutrinos in a little block, a little bubble. You put like 1, 2, 3, 4, 5 neutrinos in a bubble, and you have this bubble evolve. So in that bubble, you have entropy increasing as the number of neutrinos increasing. So then you see that they are getting entangled. And then you can actually try to go to a higher number of neutrinos and so on. Now, one thing that one finds is that the presence of spectral splits. It turns out the spectra of the neutrinos that come from the core collapse supernova or neutron star mergers are split. There is one part, there's a well-defined energy. Below that energy, neutrinos are in one group, and above that energy, neutrinos are in a very different group. There's a technical description of that, but I'm not going to go over that. So that's a spectral split. That's very sharp in the mean field of calculation. It turns out, if you do a non-mean field many-body calculation, then the split frequency is more or less the same, but the split region is broader, much, much broader. And you can also show that the entropy, the von Neumann entropy, is larger in that region. So that is to say, away from that split region, many-body description is probably okay, but at the split region, the many-body description is necessary, mean field fails. That's not uncommon. We see that kind of behavior many times in physics. So, of course, what I showed you a cartoon, and this is how the actual calculation looks like. This is already 5 years old. Now, I mentioned that there is an intermediate process. Well, it turns out if there are neutrino-neutrino interactions in a core collapse supernova where elements are being made, then there is a distinction between whether you use mean field to describe the transport of neutrinos or a many-body technique to use to describe the transport of neutrinos. There is a difference. That's not surprising. But what that means is that the capture rates of neutrons on seed nuclei also depend on whether you use mean field or many-body. It turns out the capture rates differ. This was first published, there's an update now. So considerations of these collective effects actually gives rise to a new kind of process where neutron capture, the intermediate process, the new I process. That's again something that is being actually looked for. You have to look at the sky and look at the spectra of the stars and see whether the spectra satisfy that process. There are so far about 3 or 4 stars that seem to satisfy this, this kind of process. Okay. Now, when we first talked about entanglement and so on, I said, okay, there are only 2 neutrinos, 2 flames. But we know that's not the case. There are 3 flames. So you really have to introduce a 3rd flavor. And once you do that, things change a little bit. Like this is the polarization vector difference between 2 and 3 flavors. So you can see that there is an actually significant difference. Well, the reason is, this is again something that particle physicists would like. When you have a 3-level system, it's no longer a qubit, it's called a qubit. Not surprisingly, bit versus trit, qubit, qubit. So density matrix for a single qubit, you can write in the same way as for the density matrices of a single qubit. But you replace the Pauli matrices with a Gell-Mann matrix. And then if you require the semi-definite condition, you find that there is no block sphere anymore. You don't have an 8-dimensional sphere where all the points on that sphere give you a pure state. That's a tremendous complication. The reason is the SU3 has an additional tensor besides standard epsilon ijk that we are used to in Lie algebras. It's the symmetric tensor dijk, and that introduces a nonlinearity. So then this is the completely symmetric tensor, and there's a duality and so on. And this was work with Aras Liga. Now, well, you can actually try to calculate, then once you introduce three flavors, calculation of the polarization vector and so on, and you have to worry about whether you are normal ordered or inverted ordered because you don't know which one is still the right one. So you have to do the calculations, and then it gets to be very, this is a calculation from last year, gets to be very, very complicated. Now, well, you may say, okay, that's good. Why don't we use quantum computers to do these calculations? Why do we bother with the classical computers? Well, the problem is, well, quantum computers, most quantum computers try to manipulate the so-called qubits. A qubit is a spin. So basically, you need an experiment that can manipulate spins. That's fine. That's not too difficult because a single spin you can rotate easily with a magnetic field. So it's not too difficult. But if you try to manipulate two qubits at the same time, it's like inviting a friend to dinner is easy, but inviting a couple to dinner is much more complicated because you have two schedules that interact with each other and so on. So that gets much harder. So when you try to manipulate two qubits, this is called gates in quantum computing. When you try to manipulate two qubits, you have a possibility of failing. You may not be able to do it. What they call it decoherence. What that means, that introduces a noise into your calculations. And that's why we say these quantum computers, current quantum computers, are very noisy. So you have to sort of find methods to eliminate that noise, and that's called mitigation. So noise mitigation. Of course, this is all approximate. So here is actually a calculation that we have done. Actually, we used two quantum computers. These are both qubits and qubits. We used two quantum computers, started with a state with only two neutrinos, one electron, one neutrino. And we also did two quantum computers, one at the Lawrence Berkeley Laboratory, one in Lawrence Livermore Laboratory. And you can see, if you just run the quantum computer, as compared to the exact solution for two neutrinos, you can write down exact solution. The results are not all that good because of the noise. Because of this, when you have two guys together, it's hard. So once you mitigate them, things get a lot better. But again, this is not something very reliable because mitigation techniques gets harder and harder as you increase the number of neutrinos, number of qubits. So what you can do is a hybrid approach. A hybrid approach is one where you use both classical computers and quantum computers. You use a classical computer where the classical computer works the best. You use a quantum computer where the quantum computer works the best. Well, classical computers can do time evolution very well. We do not know really how to do efficiently time evolution in a quantum computer. But the quantum computer would produce some scaling or processing advantage over the classical methods. For example, a quantum computer can calculate matrix elements of unitary operators much faster. So that's what it's designed for, really, to calculate matrix elements of unitary operators. Whereas in a classical computer, you have to, diagonalize thousands, very large Hilbert space. So for two flavors, you can just use Pauli matrices as gates. Well, because they're already unitary. Pauli matrices, of course, are Hermitian, but they're also unitary. And that's very unique, very convenient when you try to use them as gates in quantum computing, because you can make them into gates, no problem. So each qubit becomes a gate. Two qubits become a gate. When you go to three flavors, again, the trouble happens because Pauli matrices are unitary, but the Gell-Mann matrices are not. Gell-Mann matrices are Hermitian, but not unitary. You can create Hermitian and unitary matrices only in 2 dimensions. Once you go to 3 dimensions, you have to pick one. But Gell-Mann picked, of course, the Hermitian, not the unitary. So what you need to do you have to define unitary combinations of SU3 Gell-Mann matrices first in order to do any kind of hybrid approach. So you introduce, I mean, this is probably the most technical thing that I'm going to show. So you can introduce two operators, two matrices, X and Z, and then you can actually show that X is a combination of Gell-Mann matrices, Z is a combination of Gell-Mann matrices, and all the other Gell-Mann matrices you can write in terms of X and Z, powers of X and powers of Z. I'm not going to do that. But then once you do that, you also have to introduce other gates, so-called Hadamard gate, and so on. I'm not going to go into detail, just to show you the complication. So then what you do, you describe your operation in what they call a quantum circuit. So these are the two quantum circuits where you use, which you use to calculate matrix value, expectation values. And then you do the rest with the classical. Now, if you do that, life gets very complicated. And this is, for example, a result that we get. But again, you can see at the short times, everything works well. But once you run the quantum computer long enough, at long times, things go wrong. Because every time you run the computer, you are increasing the error, you are increasing the noise, and then there's no way around it. So this is where the current quantum computing is. And so I would like to summarize what I just said. Now, actually, using the mean field approximation, we have revealed a lot of interesting physics about collective behavior of neutrinos in such environments. So the deviation from many other results suggests that something special about spectral split energies, so you have to pay particular attention into that. And there is a broadening there. And this broadening happens actually worse if you introduce beyond the standard model physics, which I didn't talk about. From the QIS perspective, for simplicity, we originally included only two flavors because you can map them onto qubits and use all the existing literature, existing quantum computers, and so on to describe them. But since neutrinos come in three flavors, you really have to use qubits, and the description of qubits is much, much harder. Given the large number of neutrinos in a supernova, a complete description of neutrino transport would very likely to benefit from utilization of quantum computers. But since the near-term quantum computers are very noisy, approximate methods are inevitable. And I showed you advantages and pitfalls of one hybrid approach. Now, a growing number of researchers are working on quantum nature of neutrino transport, not just my group and many, many other people. So we should stay tuned for very interesting results. So before I finish, I would like to thank all the young people I work with. So these are my students and postdocs and young collaborators, and I really would like to thank all of them. Thank you.
Great. Thank you very much. Very interesting talk. Do we have any questions in the room? Yes. No?
Oh, yeah.
I might ask one.
Yeah.
I was going to ask more about the quantum computing aspect to describing these like collective oscillations. Is your sense is that is the field where it needs to be in terms of developments and progress in developing this technology to better describe what we would see from a supernova? Or what would you like to see?
Well, I mean, we can still try to use classical computers for many of these calculations. But the feeling is that when you go to quantum computers, some things are going to be much, much easier. We certainly cannot describe the entire supernova with so many neutrinos on a classical computer. But we can try to do many things. I mean, approximate methods give you at least 90% of the physics. But we are greedy. We want 100% of the physics, right? So then you probably need better techniques. And some of it may be better approximations for classical computers, but I suspect some of it will have to be quantum computers. At least that's my own personal belief. Other people may disagree, but that's they're going to come, so we might as well use them. Do we check the Zoom, see if there are any questions?
Next.
Okay.
We have another question in the room. Yes.
So you say the quantum computer, so what is needed? The number of qubits, other techniques, noise mitigation? What is the most important step to do those calculations?
Oh, in the examples I showed or in general?
In general.
Well, in general, you really need qubits, of course.
Yeah.
But, I mean, this gets more technical, but you can actually use existing quantum computers with qubits. But to describe a qubit with a qubit introduces qubit interactions, which means you have to really use two qubits at the same time, and that increases the noise. Eventually, if the people who build quantum experimentalists who build such computers can eliminate or reduce the noise, then probably you can map two qubits onto a single qubit. But right now, they really are very noisy to do that. Basically, the idea is this. If you have two qubits or two SU2s, from that you can form SU4, right? SU4 is an SU3 subgroup. And that's how you get the qubit. But that means you use two qubits and they interact. It's hard to get away from mathematics. It forces you. Yeah.
Thank you. Forgive a layperson question. We're talking about putting a quantum computer underground at surf to reduce the noise from cosmic rays of these qubits. Would this help this kind of research you're doing, or is it the noise inherent in the binary system of a quantum computer?
Well, it certainly would help. It certainly would help. Of course, the question is, how much easier will it make our job? That's an open question. That's an open question. But it certainly will help. I think if we can build better quantum computers and reduce noise, it certainly would be very, very useful. The issue is that there are too many particles to follow. I mean, you're following the evolution of a system with way too many particles. And in a classical computer, it's hard. I do remember very first time we tried to solve the solar neutrinos in a classical computer. Now, this MSW effect is a funny thing because neutrinos are spreading out. They are, free streaming from the core of the sun. Those are the neutrinos Ray Davis measured. But their travel is kind of classical. They move with the speed of light, but they interact with the background matter. And that interaction is quantum. So even though you should be able to do the, transport easily in a classical computer, this quantum interaction makes it much harder. When we first tried to do that on a classical computer, this was more than almost 30 years ago. I had one of those DEC stations. The older people may know what they are, but younger people will not. And the single neutrino took 4 days to go through the sun on the computer, because I had to, even though it goes next thing, it had to interact at each. It's like a politician, right? In a big space, they have to shake hands with every person. A neutrino is like that. It has to interact. But now, of course, the classical computers are much better. The same calculation I can do in this classical computer in a few seconds. So there will be improvement, I suppose, but there's a limit, of course.
Right. We have one question on Zoom.
Yeah, Dr. Jose Alonso asked, what do you expect the manifestations of these formulations to be? Distributions of element formation, energy spectra, anything measurable with our present astronomical tools?
Well, okay, that's a very good question, of course. What do we measure? We hope to measure the neutrinos directly as they come from the supernova. So like once, for example, Dune starts operating, if a supernova occurs, then they can detect it. And then, but what they can do, Dune can only tell us a single flavor. It doesn't tell us the content. It just tells there are 6 different neutrinos are coming from the supernova explosion, 3 flavor, 3 neutrinos and 3 anti-neutrinos. Dune really can detect only one of them. So it's fine. I mean, we're happy to detect just one. I'm not saying I'm not a complaint, but you can only detect one. So that's one information that you get, the spectral information. If we are lucky, we may get that. You may also try to detect the time dependence of the signal. Now that is possible to detect at detectors like Dune, but it's much easier to do in a detector like IceCube in the South Pole, because that detector it won't get the spectral information because there is a lot of noise the way it works, but it will get extremely sensitive timing information. So we will get all little peaks in the signal and so on. So that's one thing. So those are the direct detection. And then also the neutrino processes change. There's a third direct detection. I forgot, I'm sorry. That's the diffuse background. The neutrinos from all past supernova still linger in the universe. They don't go anywhere. Neutrinos do decay, but their lifetime is longer than age of the universe, so it's okay. So that background is called diffuse supernova background, and there are detectors right now trying to detect that. That also gives us a third handle, the direct detection handle. And the fourth one is detecting the elements produced in the star during the explosion. That's a third handle. That's independent of the first 3, because it uses telescopes rather than detectors, neutrino detectors. That, of course, that information also includes information about neutrinos. And you may get more information. So, for example, if the star immediately went supernova, then you have a continuous distribution of neutrinos. If the star became a black hole, the neutrino flux will be cut. So there are about 3 or 4 different handles we can have. And hopefully we are lucky enough to be able to use all these handles. Again, the luck is important because we really cannot order a supernova to explode. That's our biggest problem.
All right. We have one more question.
Hi, Baha. Thanks for the very nice talk. And I would like to ask you, what is the initial condition you assume for your simulations? Like from which state you start?
Initial condition?
Yeah.
Well, in most of these graphs, I was given what the initial condition is. Like the quantum computer calculation, we start with 1 muon and 1 electron neutrino. In the classical Q-tip calculation, we started with 3 electron neutrinos and 3 muon neutrinos, and so on. But again, these are very small numbers. I mean, because that's all you can do on classical computers. The hope is you look at this and you see a trend, and then sort of utilize that trend. That we haven't really seen yet. So there was.
Yeah. This is from Stuart Raby. Years ago, simulations of supernova failed to complete.
Sorry, can you repeat?
Yeah. Years ago, simulations of supernova failed to complete. It was suggested that neutrinos would complete the expulsion of the failed shell of the supernova. Does your analysis show that neutrinos are necessary to understand the supernova simulation?
Well, that's actually, we're talking about the explosion itself, right? Not the neutrinos, the fraction of neutrinos that come from. Now, it is true that earlier calculations about 30, 40 years ago, when they simulated supernova, it didn't explode. It's true. Well, one thing is though, those calculations were one-dimensional. So the supernova just exploding, it's trying to explode radially. Well, the second reason was that the neutrino physics was not complete in those calculations. Well, we know that neutrinos have two kinds of interactions, charge current and neutral current. Only the charge current interactions are included in those calculations. Charge current interactions only, no neutral current, and one dimensional. Then people understood the importance of turbulence in supernova explosion. You cannot have turbulence in one dimension. Impossible. How do you mix soup when you make soup? You don't mix it like this. It won't work. You mix it like this. And that is two-dimensional. You really need to go one higher dimension. So now the supernova modelers are actually doing three-dimensional models. They're not completely perfect yet because computational power is needed. But a lot of three-dimensional calculations, including all the neutrino physics, both charge current and neutral current interactions, and the three-dimensional calculations that improved hydrodynamics, improved general relativity, they actually do see explosions. So I think the answer is yes, you do need to include all of neutrino physics and all the other physics as well as you can, as well as your computational power permits you to see a more realistic explosion.
All right, thanks. Any more questions in the room? Yeah, sure.
Yeah, so you had a plot where you had compared the mean field calculation with an exact calculation for a small number of neutrinos, and the mean field result was consistently below the actual calculation.
Right.
Is there a simple way to understand why it was always below?
I wouldn't read too much to it because those are very small number of neutrinos. When you have more neutrinos, things may. What a lot of people are trying to do is developing a thermodynamic approach. So treat the neutrino gas like a thermodynamically, try to use thermodynamic arguments. There, maybe you can see more generalization of such behavior. But I wouldn't read too much yet from those calculations because they're just too few neutrinos. It just shows you that there is a difference from the mean field. The sign of the difference we have to understand better. In most of our calculations, mean field, many body physics moves in one direction from the mean field, but I would like to do more simulations in order to say that indeed is a global behavior.
So coming back to practical quantum computers, of course you want to isolate them better and better, so you reduce noise and decoherence and so on. But there's also this concept of quantum error correction. Do you know if that is being pursued for actual quantum computers that are being built?
Oh, yes. Well, as they are built, I don't know. But for the existing quantum computers, they do certainly employ error mitigation techniques.
Oh, is that what you meant by mitigation?
Yeah, yeah,
okay.
Yeah. Whether they built the quantum computers to also do it as they do the run, that I don't know.
That's what I meant.
Yeah. That I don't know. I think there's one.
I think you touched on this a little bit already, but Tom Regan asks how will the Dune LBNF project enhance the calculation of this problem?
What? I'm sorry, what?
How will the Dune LBNF project enhance this calculation problem?
Well, I mean, if we are lucky, if the supernova happens during the operation of the Dune, we'll get some information about the supernova that's happening. And we will get the spectra. We may get some timing from other, maybe ice cube and other detectors. So that certainly will happen. But it all depends on what we can get. All depends on like how close or how far the supernova is, how good the information is, and so on. Like the supernova 1987A happened before the detectors were really completed, before they were set up for supernova detection. If supernova happens while Dune is being built, then we will lose a lot of information. So we have to be very lucky that it happens while Dune is operational, fully operational, and It depends again whether supernova is how close or how far it is, so that will change the information. So we'll see. It's hard to say. I hope that they'll still see it, but just a hope.
We all hope. All right, do we have one more question in the room? Or online? All right, then let's thank the speaker again, and I have to just finish up with some more reminders. So today's talk will be available, as I mentioned earlier, on institute.surf/JBC, on YouTube and on Vimeo. And next month's John Bahcall Colloquium will be virtual event again on August the 12th, as usual, 9 o'clock Mountain Time. And as a reminder, please join us on Slack right after this talk to continue the conversation. And the link is in the chat on Zoom. And finally, we value your feedback. Please take a moment to complete the short survey you will receive in Zoom and by email. Your suggestions on future speakers and topics help ensure that this series remains relevant and useful to the community. Thank you all for joining us today, and see you next time. Right.